19. All right, so 3 more. All right, so I guess the other 3 will just catch up to us. I think they're still doing something, or they have their own things that we still need to do. Anyway, so we will start now our discussion on Module 1, Part 3. So again, before we start, do you guys have a question or a clarification?
None po.
All right. So again, feel free to ask me anytime if ever that you have a question. All right, so start with, we have here the quantifiers. So last meeting, we have discussed the loss of logic, connectives, the symbols, and so on and so forth. Okay, but that one is still lacking to have a complete proposition. Okay, so logic using propositions are incapable of describing most or maybe some of the statements in mathematics and computer science, such as the use of variables. So that is why we have quantifiers to add variables. So we can have 1 variable, 2 variables, or 3 variables in a statement or a proposition. So again, as we all know, a propositional function, or p of x, is not a proposition until it has a truth value. Okay, so if we don't know the value of that proposition or of that variable, then that one is just a propositional function. Okay, it will never become a legitimate proposition or a legitimate statement. So up to this point, we could only do this by assigning a value to such variable or to our variable. So for example, take a look on this one. So if p of x represent x is greater than 0, this will never be ever a proposition unless we have uh, a true value for this x. Okay, so never, you know, uh, even though this one is true or false, so this one will become a proposition if this one now has a final value. So for example, find the truth value for p of 4. So assuming that the value for x or this proposition is 4. So if we replace this x by 4, then we could say that this statement now is true. Okay. And since we can now say that this one is true or false, then this one now is a proposition. Okay. So we have 2 types, or 2 ways rather, in turning a propositional function into a proposition. So we have here universal and then existential. Okay. So this is the symbol for universal, an inverted A. And then this is the symbol for existential, which is a flip letter E. Okay. So let's start with universal. So from the word itself, universal, it's talking about everything, okay, or all. Okay. So this one is universally quantified statement. So we have here the universal x, which is p of x, wherein universal x, or this inverted a, is the universal quantifier, and then this p of x is just the proposition. Okay, which means that this universal, for every x, p of x is true, or for any x, p of x is also true, or for all x, p of x is true. So that's or those are the ways on how to read this universal quantifier. Okay, so as you can see, in every value of x, p of x should be true, or any value of x, p of x should be true, or basically all of the values that is possible that we can substitute or replace this x. So it should be true to make this proposition true. Okay, so hearing the word universal, so you might already have an idea for that one. So you can read universal in 3 ways, which is okay. So we have this scenario wherein universal x, p of x is true if p of x is true for every x in its domain. Okay, so if there is at least one x that is not true, okay, then that one is already a false statement or a false proposition. Okay, so that is why in here the opposite here is if there is at least one false for at least one x in its domain, then that is already false. Okay, so in universal, all of the possible variables or values for x should be true to make it true, okay, all throughout. Because if no, then that is not a legitimate true universal. Okay, so moving on, we have here existential quantifiers. So this is, you can say that this is the opposite of the universal, wherein it symbolizes by this one, wherein it's again flip letter E, wherein this letter E is the existential quantifier, and then P of X is just again the proposition. So you can read this one as for some X, or for at least one X, or there exists X. So all of those three are saying that there should be at least one, or there should be some, or there should be one false or one true on that statement to be called an existential. Okay, so just take a look on this scenario. So existential X, P of X is true if P of X is true for at least one X in its domain. So we only need one, okay? But take note, the other should be false, or the other should be true. So it should be a mix of true and false, okay? Because if every X is already true, then that is not already an existential. That is already universal, okay? So in here, for us to be able to say that this one is a true existential, there must be one true and then one false. Okay, so that is the minimum requirements for us to be able to say that it is an existential statement. And then the other one is if, of course, uh, existential X, P of X is false, if P of X is false for every X in its domain. Okay. So if there is no true values in every X that you're going to substitute, then that is not also an existential quantifier. Okay. Again, the minimum requirement is to have one true X and then one false X. All right. So did you guys get the idea of the universal and then existential quantifier?
Yes, sir.
Yes, sir.
Or
Yes, sir.
that's good.
Yes, sir.
So just let me know if you guys are confused between those two, okay, so that I can explain it more to you. All right, so if no one is confused, then let's proceed to the next one. Okay, so we have examples here for quantification. So validate the following quantified states. So number one, for every real number x, x squared is greater than or equal to 0. So in here, it's saying that this one is universally true, okay, in this kind of expression. So is this true or false? For every real number of x. So just to remind you guys what is a real number, so actually it's any number, okay, that you can think of. So it could be rational, integers, whole numbers, or even irrational numbers. That is under real numbers. Okay, so is this true or false?
Mm.
Why? What is that number
Mm.
that will make it false? Anyone? So if you can find an example, at least one value, we call that one counter example. Okay. So if you can at least find one counter example, this one is already false. But if you cannot find any counter example, then this one is true. Simple as that. So what do you guys think? Is this true or false?
True.
True? So who's saying
Yes,
here
sir.
that
True.
number one is true? Do we have an answer of false? Anyone? All right, so I guess none. So are you guys saying that number one is true?
Yes, sir.
Okay, so number one is universally true, and then existentially false. Okay, or basically you can just say, this one is true. Okay. I'm just stating that one if it's universally or existentially. Okay. How about number two? For every real number x, If x is greater than 1, then x plus 1 is greater than 1. True or
True.
false?
True, sir.
So number 2
False.
is
True.
why false?
Ay, true pala, sir. True pala. Sorry.
Take note, yes, we have the condition every real number x wherein it's under negative and positive values. But we also have this second condition wherein it is saying that x should be only greater than 1. So 2 and above. So you are going to start here with 2. So 2 plus 1 is 3. So it's already greater than 1. And above,
Okay, sir.
and then we'll just make this one super true. Okay, so number 2 is true. How about number 3? For every real number x, x squared minus 1 is greater than or equal to 0.
False.
False, sir.
False, sir.
Why? What is that number that will make this one false?
0.
Yeah, you're right.
0.
0 is also a real number. So if you're going to replace this x by 0, then 0 squared is 0 minus 1 is negative 1. Wherein negative 1 is not greater than or equal to 0. So that's making number 3 a false statement. Okay. So in here, this one is existentially true, okay, but universally false. Right. So I hope you're getting already the idea of the usage of universal and then existential. Anyway, so yeah, that's how easy to identify a statement using for kind of this reading wherein for every real number, for all, or for some, okay, or for at least one, and so on and so forth. Okay, so depending on the structure of the statement. Anyway, once you're done in understanding this one, then you can now proceed and answer our statement. Okay, so this one is only answerable by true or false. So supposedly, okay, if we are in a face-to-face format, I would ask you guys to have a counter example if ever that this one is false. Okay, but since we are in online distance learning, so I will only require you guys to answer this one using true or false. Okay, so you don't need to defend your answer if your answer is false. Okay, so just like what we did on the first 3 examples, just answer this one using a true or a false answer. Okay, so are we clear so far? I hope you guys have already actually answered this one since I have uploaded the module 1 part 3 ahead of time. So you guys have already an idea that we're going to do this one on your module. I mean on your canvas. Okay. So do you guys have any concerns regarding with this break, or is this clear? So no question.
No question, sir.
All right. So just answer this one on your canvas later on. Okay. Next one is having multiple quantifiers. Okay. So you can actually have multiple quantifiers on a statement. Like for example, you can have a universal value of x or some values of y or existential y for the proposition x and y. Okay. So you can read this one as for all x, there exists a y such that p of x and then y. Okay. Or you can have the other way around, which is having a existential x and then a universal y. So you can read this one as there exists an x that for all y. Okay. So I know that this kind of way of reading this statement is maybe different on how you construct your statement or sentence. So it's okay as long as you could say that you have a universal x and then existential y and then existential x and then universal y. Okay, so we are not in English subject, so I'm not that strict when it comes to constructing your own way of reading such expressions. Okay. Anyway, so that's it for multiple quantifiers. Next, we have here negation and then quantification. So just take note on this one. Okay, when we say negation of quantifiers, the parenthesis is not or doesn't actually matter. Okay, so if you negate a quantifier, you're going to negate all of the values inside of that quantifier. So what do I mean by that? So later I'll give you guys an example on what I am talking about if you're going to negate everything. Okay, so this one means, if you're going to read this one, means there does not exist even one x in the universal set that makes p of x true. Okay, so you can disregard this one, but if you want to analyze this one, then please do so. But you can disregard this one, okay? Because this is just a way on how to read such expressions. So if you're going to negate this one, so this existential will become universal, and then this positive p of x will become a negated p of x. Okay, so supposedly, if it's with the use of distributed properties, okay, so we will only distribute this one on the outer parenthesis. So it will not affect your inner parenthesis anymore if we are solving this one in a manner of, common math, or just like what we have learned in algebra. So in here, parenthesis doesn't matter. Okay, so basically you're going to negate everything. Okay, no, nevertheless, of the counts of your parentheses. Okay, so that is why you have to negate this one, and then you have to negate this one also. So that's how we've come up with this equivalence logic. Okay, so if you negate this existential, it will become universal, and then if you negate this positive, of course, it will become negative. Okay, the same with this one. Okay, so means p of x is not true for all x in the universal set. So again, if you're going to distribute this one, this universal will become existential, and then this p of x will become negated p of x. So can you guys follow so far?
Yes, sir.
Yes, sir.
Yes, sir.
So again, you can disregard this one, okay, because those are just ways on how to read such expressions. So this will just make you confused, matters if you're going to analyze this one. So just focus on this one. So if you negate existential, it will become universal. If you negate universal, it will become existential. Right, so let's have examples. So we have this expression, and then as you can see, here's a step-by-step process on how we've come up with this final result. So the first step, so we've distributed this one into the first parenthesis, which is this one. So again, this universal will become existential. Then again, so that you can follow easily. So the highlighted yellow is the changes from the past solution. So from here, we've changed this one. So this is our first step in negating such expressions. Next is, again, of course, distributing this one onto the next statement, wherein making this existential into universal, right? And then the last one is distributing this one onto your p of x and y, making this positive into negated p of x, y. Okay, so now we could say that this one is equally or logical equivalence with this one. Okay, we've just simply negated everything. Were you guys able to follow and how we come up with this result?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so very good. So this one is super easy anyway. So number two, okay. So in number one, I've showed this step-by-step solution on how we come up with this result. So number two, I will not show the step-by-step solution anymore. So all you need to do is basically negate everything. Okay. So this existential will become universal, and then this universal will become existential, and then this positive will become negated p of x. Okay. So did you guys get number two?
Yes,
Yes,
sir.
sir.
All right.
Yes,
Yes,
sir.
sir.
Very good, very good. Okay, so let's have an exercise. Okay, so we have this proposition. Okay, so this proposition now is a readable statement wherein we have universal x is an element of proposition n, wherein this n is actually have this readable proposition x value, wherein x is prime, or if x is prime, then x squared plus 1 is even. Okay, so again, we have here negation. So basically, we're just going to negate everything. Okay. So here's the first step. So distribute this one on the first statement or the first parenthesis. So this universal will become existential, and then what else? And then we're going to negate the proposition, okay, or the readable proposition letter X. So as you can see right here, if we're going to distribute this negation into the first statement, yes, it's doable. Like for example, this one will become X is not prime, but we cannot find, or there is actually no negated value of conditional. So that is why we're going to apply the laws of logic, wherein this P conditional Q is actually equivalent to negated P or Q. Okay? So you have to convert this conditional first into or into N. Okay, because that N can become or that or can become N. Okay, do you guys what I'm trying to say? So you cannot negate this one directly. Okay, so you have to find an equivalence in the laws of logic wherein this one is equal to or this one is equal to N. So any of those two. Right? So in here we've just found out that this P conditional Q is actually equal to negated P or Q. Okay. So if I'm not mistaken, this one is number 18 in laws of logic, 18 or 21. I'm not pretty sure. Anyway, so you can find this one in the laws of logic. Okay. So from here, we can now convert this one into this kind of expression. So yeah. So our negated value or negated sign is still in here. And then we're just going to follow this one. So this one is the letter P. So in here, it's now negative. So we should follow this one for now. So X is not prime. So from positive to negative, wherein we just added not. And then this or, so from condition to or, so just put here or, and then just copy the last one as it is, which is X squared plus 1 is even. Okay. And then from there, you can now start distributing this negated symbol. So from negated P or Q, so this one is equal to not P and not Q. All right. So again, from X is not prime, okay, just negate that one again, and then you're going to go back on the original statement wherein X is prime. Okay. And then this or will become N, which is now this one. And then the last one will be negated. So from this to this. So as you can see, we found that even, so the opposite of even is actually odd. So you cannot just say that X squared plus 1 is not even, okay? Because we can answer here, let's say, you're actually trying to make the possibilities into a larger domain. Because in here, we're just saying that this one is even. So what is the complete opposite of even? That is odd. Okay. So do not just say here is not even, because if it's not even, then we can also answer integers or fraction or even pi number, okay, or any values. Okay. So for us to to have a perfect match, what is the opposite on what is the opposite of even? So we should find any possible, okay, equivalence or opposite rather of that word. So in this scenario, the complete opposite of even is odd. Okay. So that is why this one now is equal to this one. So X is prime and X squared plus 1 is odd. Okay. So did you guys get it so far?
Yes, sir.
How about the others?
Yes, sir.
Yes, sir.
Medyo, okay. So again, I think the only tricky part is this one, okay? Because maybe some of you or most of you will say here, let's say the negated value of this one is X squared plus 1 is not even. Okay, so do not do that one. If you can find a straight opposite of that word, then please do so, just like this one. The opposite of even is odd. Right, so let's have another example wherein we have this expression, and then we have to negate everything. So again, this existential will become universal, and then the SQ proposition will be negated. Okay, so we now have here the negated symbol, and then if you're going to distribute this one, so it is possible, since we can negate this greater than, we can also negate this and then we can also negate this equal. So from here, so what is the complete opposite of greater than? So you can say that it's less than or equal to. Okay, so if ever that you have answered here less than, I will also accept that one. Okay, so you can answer here less than or equal or just simply less than. Okay, so no problem. Okay, so that is the opposite of this greater than. And then the opposite of and is of course or, and then the opposite of equal is of course not equal. Okay, so simple as it is. We now have the negated result of this number 2. Did you guys understand this one so far?
Yes, sir.
Yes, sir.
All right, very good. So again, if you have a question or clarification, so feel free to ask me anytime. Anyway, so once you're done in trying to understand what is the negation of this expression, blah blah blah, so you can now answer these citrics. So I only gave 5 numbers. Okay. So yeah, I'll leave this one into you guys, and then I guess it's possible. All right, so answer this one using Microsoft Word, because we can also find the symbol in Microsoft. We can also find the symbol in Microsoft. So I guess no problem. So for equal, you can also find the not equal, and then for plus. Right, so take note, you don't need to change the x plus 3, x minus 3, x plus 3, and so on and so forth. So all you need to change is the equal, and then the other connectives, which is the and then the or, and then the greater than or less than. Okay, so those only. Okay, so no need to change the plus and minus. And then where can you find the other symbols? So just go to insert. So it's just the same in Microsoft Word. So go to insert and then click this equation, and then you will see those symbols. So we have here the not equal, less than, greater than, less than or equal, greater than or equal, the flip E, which is for existential, and then where is the universal? Universal. Can you guys see? Where is the inverted A?
Upper right, sir.
Upright, sir.
This one. Yeah. Okay, so this is for the universal. All right, so this one is doable in Microsoft. All right, so any questions so far regarding with your seat work?
None, sir.
None, sir.
All right, that is good then.
None.
Next, we have here Brooks. So this one is actually an argument that establishes the truth of a theorem, which we have already did many times, like for example, using a truth table, okay, or using an equivalence rules, or even using inferencing rules or deductive. Okay, so in Brooks, of course, there is always a hypothesis into a conclusion. Okay, so that is why we call that one proofs. Okay, so what is this equivalence rules? So this one is describing that logically equivalence is equal to this logical equivalence rule. You're saying that this one is equal to this expression. And then what is this inference rules or deductive? So this one is described when a weaker statement can be deduced from a stronger statement. So in inferencing rule, this one actually can be done, like for example, by having 5 variables or 5 hypotheses, and then concluding that this one can be concluded by using 1 variable or 2 variables only. So from 5 hypotheses into 2 conclusion or 1 conclusion. Okay, so I'll give you guys some examples on how to do inferencing. But for now, So take a look on these equivalence rules, wherein we're saying that this one or this expression is equal to this expression. So as you can see, we have here negation, implication, De Morgan's laws, commutative, associative, and so on and so forth. Okay, so those are equivalents. So we have already discussed those things, okay, in the laws of logic. So this is just actually just a recall, okay, wherein we can apply equivalence into inferencing. Okay, so I will not discuss this one anymore. Just try to recall this one on our last discussion. Okay, so here's now the rules of inference. So to prove the theorem means to show that the implication is a tautology. Okay, so this is one thing that you have to take note. This is very, very important. In rules of inferencing, all of your hypothesis is concluded or assumed to be true. Okay, so for example, if this one negated P, if we have that kind of symbol negated P, the value of that one is still true. All right, unless there is another hypothesis wherein it is saying that that true value or the true variable is actually false. So the only thing that can make that hypothesis to be false is another hypothesis, or with the statement of another hypothesis. So if there is no another hypothesis that is saying that this one is false, then we assume that negated P is actually true. Okay. So yeah, I know this one is quite confusing when it comes to rules of inferencing versus the laws of logic, or the using or with the use of truth table, because that negated is like nothing. Okay. So you still read that one as a true value, or that one is still a true value. Okay, that's why we call this one a tautology, because in every result, in all of the hypotheses, in all of the conclusion, the entire statement will become a tautology. Okay, so like for example, this expression is a tautology. Okay, so we have here the P conditional Q and then P and A, okay, which came from this expression. So this is the proof wherein if you're going to combine all of those with all of the possible combinations, so true, 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 false, false, true, false, false, all the results that you're going to get are two, okay, or just simply a tautology, right? So as you can see, we have here this expression, and then if you're going to read, to write this one into inference format, so it would become like this. So how did we write this one, or from this one into this one? So if you can see a symbol N, that one is like a separation into another hypothesis. So that is why we have this letter P to here, and then N is a separation, which is now another hypothesis, which is P conditional Q. And then the last one is conditional, wherein we could see that this hypothesis is equal to Q, or concluded as Q. Right? So that's how you read this one into, or that's how you convert this one into this one. Anyway, we will continue this one later on, since I guess we now only have 10 seconds. So goodbye for now, and then just wait for the part 2. All right. So bye-bye. See you on part 2.